So I will just say that these are the best two ways to get hold of me if you'd like to. If you have any other questions that you did not think of during the presentation, either LinkedIn or Hotmail. Probably it'll be faster through LinkedIn. In any case, how many of you feel that you are perfect, really great with recursion, and you're here just as another night, whatever?
Heck no.
Okay. I assume, yeah, I assume no. How many of you feel that you have done recursion before? This is just a refresher.
No.
Okay. So I assume that everyone is would like coming from zero. Would that be accurate?
We have a more zero than hero response.
Okay. Excellent. So I would like all of you who just felt that you're coming from a no recursion background to be able to lead a problem. There is no reason that after this presentation, recursion is not my day job. Okay, fine. So Kirk, I'd like you to be able to, at the end of the presentation, to be able to do recursion naturally. So all of you, please either volunteer or allow me to volunteer you to lead a problem. The recursion is not a big deal. Somewhere close to here. Oh, good. Rowan, excellent. So, okay, I think you understand what I'm asking. I will go with the first slide, and it did not go. Okay, here we go. So in the agenda, we will go through another color commentary. If you have either comments about the presentation, even if it's a negative comment, please do share it with me. So we will go through the what. Let me see if I can change the pointer. Laser pointer. Great. I have two of them, even nicer. Do we know how to stop the hide presenter view? Yeah, let's do that. Okay, now one pointer. So we will go through what is recursion, why we do recursion, and how does the compiler does it. We'll talk about tail recursion versus left recursion. And then the last slide will be tree processing, especially binary tree. The last two slides, I will not go through them. They are, if you are familiar with induction, mathematical induction, and you've never done recursion, then the last two slides simply point out that induction and recursion are the same animal, but going through the same process in reverse order of each other. There are 5 GitHub repositories. The first one is this presentation. Then recursion 1, simply just not to have the same name, is the fully developed, including solution of the recursion problems. Stripped is the same problems, but I stripped them of the solution. That would be the one we would use for the exercise today. Then tree processing would be binary tree processing, and again the stripped one would be without the solutions. I will drop the link. Great, thank you. So what is recursion? A recursive solution is broken down into 2. You need a terminating condition and recursive logic. The same logic that applies to solve n items will also solve n-1 items. And the moment we got to 1, this is the terminating condition. So here's an example. N factorial is defined to be 1 times 2 all the way times n. So factorial of 1 is 1. The factorial of 2 is 1 times 2. Factorial of 3 is 1 times 2 times 3, and so on. I'm sure everybody has seen it. A recursive definition would be n factorial is also n times n-1 factorial. This is true all the way down to 1, where If n is 1, the factorial of n is also 1. So then it is true for all the rest of the numbers. And again, if anybody feels that I said something that they don't understand, or I'm going too fast, please slow me down or tell me where you misunderstood whatever I'm saying. And here's the C# definition of factorial of n. If n equals to 1, we return 1. Otherwise, we will return n times the factorial of n minus 1. Does everybody see it?
I have a question. So just in the example, you have the recursive definition and the terminating condition. When n is double equal 1, then n factorial double equals 1. So the recursive, the terminating condition, is that always like have the I guess in this example, because you're using n factorial in your terminating condition, but that's part of like this recursive logic. Like you're using kind of the logic to create your terminating condition. Is that usual?
It's a must.
Okay.
So let's go through it as if we're a computer. If n equals to 2. If n equals to 2, then we do 2 times the factorial of 1. The compiler will go back and call the same method again, but now with a 1. And if we did not have the terminating condition, we will continue forever. The terminating condition stops the recursion. Did I answer your question, or did I not understand your question?
Yeah, so what we have in that C# code is your terminating condition just in like a method, right?
I'm sorry, ask me again.
What you have in that C# code snippet right there is your like displaying your terminating condition in a method, because it has like that if then.
I could have split it into 2. I could say if n is equal to 1, return 1. Otherwise, return n times the factorial of n minus 1. But maybe that's not your question.
That is, yes, that is my question. So you answered it. Thank you.
Yeah, I think you might be getting a little thrown off by the ternary operator. If you put kind of parentheses around it in your head, it might kind of make more sense that you're not actually calling factorial in the terminating expression or the guard expression. It's getting called in the return statement.
If I will stop this present, Megan, are you okay? Megan, are you okay with that explanation? Would you like me to spell it out? The only reason I didn't spell it out is because the moment I'll add lines, then the whole text becomes smaller. I wanted it to be font 26. Oh, here, I can write it. Yeah, beautiful. James wrote it. James wrote that, yeah. If n equals to 1, return 1. Else, we don't need the else because of the return, but else is just as good. Return n times factorial of n minus 1.
Yeah.
Does it answer your question?
Yes, it does. Thank you.
Oh, good. Okay. So the above
color commentary.
Say it again, James.
That's what I meant by providing color commentary.
Excellent. Thank you. So the above factorial has got one problem. If you look at it, if we start with n that is 0 or minus, then this will never terminate. Next example of a factorial, I will show you what I've done. And there is an easy way to do it as opposed to checking at every iteration if n is less than or equal to 0. And another comment is that usually if you see the factorial in literature, if you noticed in here, if n equals to 1, then this is 1, and 1 factorial is 1, equals to 1 times 0 factorial. So 0 factorial is 1. And therefore, most places who show factorial as a recursive call have a terminating condition that is 0. If n equals to 0, then we return 1. Otherwise, we do n times the factorial of n minus 1. However, I have never in my life worked with a 0 factorial. It's only of academic interest to me at this point because I've never encountered it in real life. So, and I wanted to keep it simple as opposed to the mathematical minutia. Just have it, the translation from iterative to recursive. With that, I will continue unless somebody would like to stop me with another question. Going, gone. Okay. And the screen did, here we go. So why use recursion? Every iteration can be written as a recursion, but it's not the case that every recursion can be expressed as an iteration. An example is a binary tree. In order to traverse a binary tree, if you try to do it in an iterative way, you'll quickly see that it's not simple. I'm not saying it's impossible, but it's not simple. And when you try to traverse it iteratively, you will need some sort of a stack to do it. If you do it recursively, it's quite simple. And we will see the last slide that we'll go through, we'll see an example. So how does the compiler does recursion? The compiler implements a recursion using a stack. The same stack that the compiler is used to keep track of method calls, it is using the same stack to keep track of where it is, how many times it had called itself. Any questions about that? This is very hand wavy. Any question about that? Okay. At a recursive call, what the compiler does, it takes all the local variables and the return address of the method and pushes them on the stack. So now we have a big frame of the local variables and the return address. Upon return from the call, the compiler pops this complex frame, rehydrates the local variables, and continues from that point on, continue with that right after that recursive call. Is that clear?
I have a question.
Fire away.
I have heard that term hydrate before, and I get the sense of what it means, but could you define that?
Sure. So we have a variable, local variable, and we popped the frame out of the stack. So now we assign the variables that the stack has of the local variables, we assign them to the local variables. And that's what I mean by hydrate the variables. We take what the stack used to have and assign it to the variables. And now the variables are as if the recursive call did not happen.
So is it kind of like there was almost like a placeholder there before until the local variable was hydrated, or it was just like undefined?
Those local variables were used in the next, if you think of a stack, let me see what happens in next. Yeah. If this is our stack of recursive calls, at each recursive call, the variables take different values depending on n minus n, then n minus 1, then n minus 2, and so on. So when we come back, in our case, there's only one variable. So we hydrate only one variable with its previous value, and in our case, it's n one more than the called stack.
Mm-hmm.
Okay, let me go back. Previous. Okay. Does anybody else have any question about this?
Yeah, I have no idea what you mean by top frame is popped.
Did I write that someplace? Top frame, here it is. So let me go back to the next frame. So if in this case, I chose 2, but if there's n a large number, at each call to the recursive call, if we think factorial of 5, let's say, so there would be 5 times the factorial of 4. In order to do factorial 4, we will need to put in the stack the 5 and the return address. And then we go and we calculate the factorial of 4. To do the factorial of 4, we need to store in the stack frame 3, and then we do the factorial of 2. So when we come to do the factorial of 2, we will need to store 2, the return address, and do the factorial of 1, which is 1. So then we come back here, we pop the frame, factorial of 1, we do not store it. But at this point when it was 2, then this frame is going to be popped, meaning we're going to take the values of that frame. That frame is no longer going to be in the stack. Do you understand what I'm saying, or am I talking a lot? Do I need to write it down?
So Avi,
Yes.
in that example you just made, when we get to that factorial of 2 and then to the factorial of 1, we already know what that value is 1 because that's our terminating condition, right?
Correct.
So then we can use that to figure out the factorial of 2, and then basically getting the value means popping the frame.
Stack. Correct.
The
The
stack.
frame.
Okay.
Correct.
And then you use that to go back to 3, factorial 3.
Correct.
Okay. So it's kind of like each time you get the value of the one before it, you're popping the next frame off the stack.
Correct. Who asked me that question? Is that clear?
Do you mind if I provide a slightly alternative explanation?
Yeah,
and
absolutely.
Please correct me.
Absolutely.
So a stack frame is kind of a local function context. Like you've got one stack, and when it calls a function, it creates a kind of new frame on that stack, which
Correct.
is the context of that function call. It's a little confusing because it's like, what's a stack frame? What's a stack? How is that different? But really, it's just kind of the CPU is using that space in the stack to do a kind of local function context.
Is everybody clear with that explanation? Shall I drop off the presentation and do something on Notepad or something like that? Whoever asked me that question, is that clear?
I asked you, but I'm like right
Robert.
up front. I'm not a math guy. I mean, you know, I've gone through some coding stuff, but I don't want to slow the whole group down just because I'm not a math guy.
This is not this stack is not mathematics. Stack is a computer data structure.
Well, but I'm also, I'm probably less experienced than a lot of folks here. So again, I don't want to slow down the group because I'm.
Tell me, did you understand it or not really?
No, not really. And
okay, hang on.
like
let me stop the share. Not the share.
Let Kirk take a crack at it real quick. He's pretty good at putting things in.
Kirk, do you want to do it?
Terms.
Do you want to present?
I totally think someone drawing something would like help. It's hard to wrap your head around, but it's a really important thing to kind of understand before we kind of figure out more.
I just want to hear what Kirk has to say really quick.
Yeah, and I think a drawing could be perfectly okay. But I think for the purposes of this presentation, and I think like just for like general programming knowledge, the way I tend to think of it is every time you run a function or call a function, that function goes on the stack. So the stack's just the computer sort of like storing the values of it. And when the function finally returns a value, it is popped off the stack. So you call a function, it goes on. When it's done and it returns something, the computer's like, okay, this function's done. I can take that memory back. Gets popped off the stack.
So, and by pop, is it like, well, I learned, I guess it was in Python or something like that, where you could, there was like pop meant, there was like pop and, I think it was pop and push or something like that. Where
It's a very similar concept. So if you think of the stack as just like memory that you can put the functions you're working on, it's like every time you call a new, so let's say you're in function A has to call function B. So function A was on the stack. Hey, I hit B, B has to go on the stack. Hey, I hit C, C has to go on the stack. Okay, C's done, returns a value. So I can take C off. I don't need that. I don't need to allocate space for it anymore. B's done, I can take B off. I don't need space for it anymore. A's done, and that's all the stack is. So it's what we call like a last in, first out. The last thing that hit the stack is the first thing that comes off. That's why I say it's popped off. It means the function is done, it's returned a value, the computer can take that memory back. You know, it can get it off the stack. So it's very similar to a list in the way that you add them on as the application goes on, and when they're done, it takes them back off. So in the context of this recursion, every recursive call is a new function call. So it's a new function that's got to go on the stack. But as soon as the first one resolves, like a cascade, it goes back down. Oh, got the answer, return, pop it off. Got the answer, pop it off. Got the answer, pop it off, and kind of come back down.
Okay.
A kind of like classic example would be if you wanted to convert 1 + 1 to kind of stack-based code, you would push 1 to the stack, you would push 1 to the stack, and then you would call the function plus, which pops 2 from the stack and executes it in a kind of new stack frame.
Oh, okay. Thank you.
Can you see my notepad?
No, we can't. We see your PowerPoint right now.
Okay. I will stop sharing for just a second, and I will share my entire screen as opposed to just the share the entire screen. Now you see my notepad.
Yeah.
Yes.
Yeah.
Okay. So if we have factorial 5, then the return of factorial 5, I'm ignoring the terminating condition. It is 5 times the factorial of 4. For the compiler to do the factorial of 4, it cannot forget the 5. So what it does, it will push 5 and the return address of this point of where it was, the function, the address of where it was in the factorial. And then it can go ahead and call itself, but now with 4. So it will override 4. It was n used to be able to equal 5. Now it is 4. And somebody's telling us something. Did anyone else audio get quiet? Might rejoin. Rowan, do we need to wait for you?
You can just keep going, Avi,
Okay.
because we're recording this. So.
Oh, good, good. Okay. So, Megan, you'll look at the chat.
Yeah. Yep. I'm on it.
Okay. So we pushed 5 and the return address of where we were, and then we flipped n from 5 now to 4, and we're trying to do the factorial of 4. Again, I'm ignoring the terminating condition. So we do 4 times the factorial of 3. In order to do the factorial of 3, it's the same function. So we push 4 onto the stack, and we end the return address of where we are, and we do the factorial of 3. The function calls itself now with 3. So we override 4 with 3. And here's 3 times the factorial of 2. Same deal. We push 3 onto the stack and the return address of where we are, and we do a factorial of 2. Factorial of 2, same deal. And now we come to factorial of 1. This is our terminating condition. So it is 1. So now we come back. In order to come back, the compiler will pop the this stack frame. So it knows where to go to because of the return address, and it will assign, it will rehydrate, and now will become 2. No matter what it was before, now it will be 2. And we will, at this point, we know the factorial of 2. It does 2 times whatever the factorial of 1 is, and we are done with the function. So we will pop this frame off. So it knows where to come back because of the return address. And now it will rehydrate n. No matter what it was, now it will become 3. And it will do the same thing for this. And doing that, we are done. We can return to whoever called it, whoever called us. Is this clear?
I guess. Yeah, I mean, I'm along for the ride, you know, so we'll probably clear up as we go.
Tell me what you don't understand out of it.
Or you don't put me on the spot, man. Don't put me on the spot.
I think like this is just something like sometimes you need to take a little bit of time to soak in. I think like having that the different explanations, like Kirk related it to some other things, and we had Rowan explain it in a different way, and then you went through with that very technical but visual thing. I thought that was like a nice follow-up. And then, like I said, we have the recording, so people can go and watch it again. And you know, as we go through the practice problems, it'll probably become a little more clear. Karen, did you have a question?
Actually, I had sort of a simplification of Ari's explanation. Ari, can you pull up your notepad again? And maybe I can help. So Robert, what's happening is
Karen,
he's running.
Let's not do it. Let's continue.
Okay,
Robert
sorry.
also already pointed out that he prefers that we'll continue. Let's continue.
No.
I do believe that you have simplification. You can write to me about it. It will help me probably with the next presentation. Okay, my point here is because we're using the stack frame to push and pop frames, a recursive solution is more expensive than the iterative solution. Let me just see if I can get rid of this. Megan, I know you're taking care of it. The recursive solution is more expensive than iterative solution, except for a tail recursion. So let's take a look at the tail recursion. Okay. So this is the solution where first we take care of the value of the fact that if n is less than or equal to 0, we will not call our factorial helper. Whatever we saw before as factorial now is factorial helper with a one-time check to make sure that n is greater than 0. Now, in the factorial helper, we have an option. If n equals to 1, the terminating condition did not change. But for the recursive definition, we have 2 options. Option 1 is n times the factorial helper. Option 2 is factorial helper times n. Everybody sees that these 2 are identical except for the order of the operation. I assume silence is yes, everybody sees it.
Yeah.
In option 1, the recursion, factorial helper, this is the recursive call. The recursive call is the last thing that happens. Notice that the return address is the very end. In here, the factorial helper is not the last thing. In here, we pop the stack off, rehydrate n, and then throw it away because we return. In here, we pop the stack off, rehydrate n to what it used to be, and it's a good thing we did. Otherwise, we will multiply by the wrong thing. In here, there is no need to rehydrate n. We're going to throw it away. So the compiler will return your tail recursion into an iteration. Did everybody understand what I just said? Any questions? If it's silence, I will assume everybody understood and I will continue. Going once. Is that a question?
That was a yes.
That was a yes, you understood. Okay, I will move on. It does not like, oh, here we go. Left recursion is when you do the recursion ahead of time. Sometimes the problem demands a left recursion. The place where I've seen a left recursion is when you're trying to translate a string into an expression. So if we have to do, think of yourself as the beginning of a compiler process. You need to take the elements that are presented. In this case, our compiler is very simple. It understands numbers and operation, and the operation are either plus or minus. No spaces, no anything. So just, we have an expression, which this is an expression. It can have a plus or a minus to it, and a term. A term is a number. Everybody understands it? Here's the definition of an expression. An expression is an expression plus or minus a term. So 5 minus 3 minus 1, we would like to do 5 minus 3 first. That's why it's a left recursive process. Does everybody understand this example? It's supposed to be simple.
I'm not sure about, I haven't seen that syntax with the 2 colons followed by the equal sign.
This is a definition.
Okay.
It's a grammar rule. It's called BNF,
Yes.
Bacchus NOR form.
Yes.
It's very in depth.
Could you please write that in the chat if you know how it's spelled, because I have no idea just hearing it from you. Thank you.
Thanks, James. Bacchus NOR form. Okay. Or sometimes called Bacchus normal form. The story is that Bacchus wrote it, and Bacchus did not intend for it to have recursion. Now was the secretary who transcribed it, and he added things to the Bacchus form and called it Bacchus NOR form. And we got recursion from that point. That was for Algol 60. In any case, let's not get bogged down with it. All I'm trying to say is expression is defined to be expression plus or minus a term. And a term is a number, a string of digits. So this is, go ahead.
The expression is also a term. That's important here too.
That's correct. An expression is either an expression plus or minus a term, or it's a term. Correct. Correct. So now, if we think about how do we translate, how do we make it into a program? If we write the algorithm for doing it, if we will write it as a recursive algorithm, such that whatever we call for expression, we call expression, then we recognize either plus or minus, and then we recognize a number, or just recognize a number. This will fail for the simple reason that this will become an infinite recursion. We call the recursive process without getting closer to a terminating condition. This is my whole point behind this slide, that when you do a left recursion, you have to be careful about the fact that every iteration or every recursive call needs to get you closer to a terminating condition. Maybe you didn't understand my example, but you do understand my point of the slide. Are there any question about the point of the slide? And again, silence, I assume, is no, it's this point at least is clear.
I think
Just to,
It
Go ahead.
it makes more sense like just reading the text than looking at the expression, for
Excellent.
me at least.
Okay. Just to finish the story, and I will not belabor, nor even if people don't understand the definition of how do we do this, I will just present it, but we will move on. That an expression can also be defined as term and rest, where rest is plus or minus expression. And now it becomes a tail recursion. Never mind. The whole point is, if you do a left recursion, just make sure that your recursive call brings you closer to a terminating point. You don't call a recursive call with the same data. That's the whole point behind that slide. I will move on. A question? I'm good. Great. Thank you, Maxwell. Okay. So the last slide is a binary tree. A binary tree is defined to have a node. In our case, it's just a number, but it can contain any data structure. A left subtree, which is a tree in its own right. So this left subtree is a tree in its own right. And the right subtree. Every node in that tree has got two subnodes. Even in here, we have two null nodes. Is everybody still with me? Okay. And so a binary tree can be traversed in node, then the left subtree, then the right subtree. This is called prefix notation. We could traverse the left subtree, then the node, then the right subtree. That's infix notation or processing. Lastly, we can process the left subtree, the right subtree, then the node. That will be postfix processing. Did everybody understand this?
So that's just names for the different order that you can go in.
Correct.
Okay.
But is it clear? So if we have to traverse the tree in prefix processing order, then one will be first, the node itself. Then we go to process the left subtree. Would anybody care to tell me what will be the next thing to process?
Shout them out. Take a guess.
Come on, guys.
Karen says R. Do you have a number, Karen, that you can give us? Oh, Cindy said 4.
Okay. Then explain to me why 4.
So wait, where are we moving from? Where are we starting?
We did 1.
Okay,
as
we're
the
starting
node.
at 1.
What will be the left subtree?
The left subtree of 1.
Isn't that 2?
Exactly. We will do 2 first. That will be the node of the left subtree. What will be the next number?
3?
It would have to be 4, since that's going to be the left of that node.
Excellent.
Okay.
That will be the node of the left subtree of 2.
Yep.
And then what will be the next number?
That's
Cindy
what
says
Karen
8.
and Cindy are both going down the left side of the tree, and so is Kirk. Cindy just jumped ahead of all of us and went down
Yeah.
the whole left
Okay.
side.
Now we did 8. What will be the next number? We did the left subtree of 4.
Miguel says 5.
Tell me why 5. Eight
Because it's
is
the
the
left.
left subtree of 4. If we're doing NLR, the next thing to do is the right subtree of 4. Does
Okay.
everybody see it?
So you only go up 1 from where you currently are and then go right as soon as you can.
Yes. Tell me why, Megan.
That was more a question. So I can't tell you, but can somebody else tell us? Does anybody know?
Well, let me try to explain. I thought this would be clear and that'll be an easy slide. We have a tree and we process the tree node left, right. We did the node 1, and then we recursively call the tree for the left side. And when we're done processing it, we will call it recursively for the right side. So let's do the processing of the left subtree, which is a tree in its own right. How do we process the tree that starts with 2? Did I speak way too much and not everybody understood what I said?
I mean, if I can take a crack at it. I mean, so we started, our node was 1 with the left side and the right side. According to the prefix, we go to the left side, node to the left side.
Correct.
So now we're in just the subtree from 2. So now 2 is now our node. So we can ask ourselves again, what's the left side of 2? Then we get that subtree just from the 4. So 4 is now our node. What's the left of 4? So I tell, like, once we've exhausted all, we can't go left anymore after 8. So we have to kind of go back up. Okay, we've done the left of 4. So now what's the right of 4? Then you get to your 9. And that's resolved. So similar to what we did earlier with the factorials and going up the stack, it's a similar concept. Except with trees, you tend to see you traverse down, and then now we're kind of going back up the right side. So after 8 to 9, back to 4 up. We've evaluated the left side now, back to 5, and then we get all the way to the right side of the initial node.
So now when we're done with the processing this subtree, what shall we do next? And I believe you understand, Kirk. I would like somebody else.
I would believe that it would be 3, then 6, and then 7. Because that would be the right, and then we have a left again, since 3 is the node, and then we go to the right of that node.
Beautiful. Could somebody else also traverse the tree for me? Stephen, would you like to?
Sure. Hold on, you're blocking it. There we go. So yeah, we would start at 1, then go down to 2, then go down to 4, then 8. Then from there we can't go left. We go to 4, we process 9, we go to 2, we process 5, go back to 1, head right to 3, then go left to 6, then go back up to 3, process 7, and we're done.
Yep. Anybody else?
I have a question
Fire away.
again. So I guess it seems like so Avi, can you move okay, thanks. It seems like because this NLR, it kind of goes in like this circular pattern. So like since we went down the left, we went to the node and then exhausted like the left side, and then so go back up to the node and go right. And it just seems like once there's like, okay, we already visited that stuff below, so we're going to keep going back up and until we can't anymore, and then go the other way until we can't anymore. I'm just wondering, we're talking about this traversal. So are we actually hitting these nodes twice when we go down and then back up? And then, so like 1, 2, 4, 8, back up to 4, down to 9. Or is that just like something we're visualizing in our head to make more sense of it?
The first person who said back up the node and then to the right, I did not bother to correct the person. but node left, right, there is no traversal of node twice. It is, so if the tree that we're traversing is 4, 8, 9, this tree, we start 4, that is the node. Then we do the left side, which is only one node, 8. And then we do right, the right subtree, which is only one node, which is 9. We don't go back to 4 to get the 9. This is what you said, it's only in our head. I did not bother to correct that mistake, but you caught it.
So really, we're going 1, 2, 4, 8, 9, 5, 3, 6, 7.
Excellent.
Because we're not hitting anything twice.
Correct. Correct.
Okay.
I would like a volunteer to do left node right. Someone who hasn't spoken yet.
Or someone can write it in the chat if they'd like to give a crack at it, if you can't use your mic.
Yeah, I can do it if you'd like. I mean,
You probably know it. You
we
said
can't
that
see
you're
when
really
you-
good at it.
We
Kate,
can't see it when you have your,
yes, I know. I
Okay.
was just trying to volunteer somebody. Kate or Stephen. If nobody would like to do it, I will do it. But I would like you guys to do it. So if we do, go ahead, Meg, you go ahead. Do
I just did
node right.
one. I know,
Then you volunteer somebody else.
Karen, I bet you can do this, Karen. If you're at your computer right
Karen.
now. Or Cindy, you're just typing in a bunch of numbers.
well, like doing this is a bit tricky because you've got to like say how you're moving, but like not process things. So like we start at the 1, but we don't process the 1 yet.
Miguel said he'll do it if
If
you
we give them sure.
first.
So if we process the left node, this is the left node. So you want to start with that? In order to process the left node, what are you going to do? Process its left node. And how do you process its left node? This is its left node. So the first number is 8.
All right, Miguel,
8.
let's see some
Karen.
magic. Miguel or Karen, let's race. Who can get it first?
Or Stephen, I think.
There's 2 Stevens. So
Both
now
of them.
it's all 4 of you racing.
Come on, guys. So if we process 8, then we need the node.
I think they're typing it in.
The node would be 4. Does everybody see it? We start with this tree. In order to process this tree, we need to process its left subtree. To process the left subtree, the first thing we do is we process the left subtree. Before we process, in order to process the left, we need to process the left of the left. That is 8.
So we have first 3 numbers, 8, 4, 9 from James.
Agreed.
So we got that much.
So we processed this left subtree of this tree. So what will be the next number?
It's going to be 2,
Excellent. John, thank you.
then 5, then we
Yes.
go up to 1. You can't go left anymore, so then we have to go down to, so it's left, I guess down to 3, and then just the 6. Well,
To process this right subtree, how do we process the tree?
Well, you jump
Left
down to 3, you don't
node
count
right.
it. You go left to the
Yes.
6, then the 3,
6,
then the 7.
3. Excellent. Did
Ooh,
everybody understand it?
that's tricky.
Okay, who's left?
Nice
Karen.
job, John.
Yes, very
Okay.
nice. Karen, do you want to do left, right node?
Oh, you put me
Karen,
on
I
the
would have,
spot.
I would have done the, I would have done the same thing as you.
So we're gonna start at 8, is that correct? Let me get my starting point correct.
Yes.
Okay, so we're gonna do 8, 9, 4.
Yes.
Then we're gonna do 2, 5. Yeah,
On this tree, we just finished the left node, the left subtree.
so now we get, okay. 8, 9, 4, 5, 2.
Excellent. So we did this. So now we're back up to this tree, and
Yep.
we finished processing the left subnode.
So now we're going.
There's a right
Then
subnode.
we've got to go, do we then go 6, 7, 3, 1?
Very good.
Oh, phew.
Right?
Oh my gosh, so proud of you.
At each point, we are doing just simply what this is. Someone. Okay. Are there any questions?
What is
Go
the
ahead. Oh, the haha was for the laptop got scared. Are there any questions? Okay. The last point I'll make about
Wait,
the tree. Go ahead.
Avi, Cindy had a question.
Yes, please fire away.
I was just wondering, like, the purpose of having to distinguish all this prefix, infix, postfix, right? Like,
It really depends on the problem that you have. Right now, when it's a single number at each node, it means nothing. But one of the interview questions I had at Amazon was I have to write the process that does the compilation, and each one of them is the dependency tree of subroutines, where it was not a binary tree, it was an n-ary tree. And how will I go about doing it? So it was a traversal where the children had to be compiled first. They're the most subroutine used. So this would be a left-right node. It really depends on the problem at hand.
could you give like a specific example, like maybe like a scenario for each processing?
Right. So let's say we have a tree which are routines or libraries that this is a dependency of the libraries on each other. So this library depends on these two. That library depends on these two. This library depends on this two. That library 3 depends on library 6 and 7. So if you compile library 1 before you compile library 2 and 3, you may encounter errors because these two are not compiled yet. So you need to compile these two libraries first before you can compile that library. Did that make sense?
Yes, if that's the case, which processing would you use?
The left-right node.
Kirk, did you have examples or did you have a question?
An example. The one is, I'm only familiar, I'd never sort of examined the infix and postfix before, but I know like prefix can be a kind of a straightforward way. Classic example is like finding numbers in a dictionary, finding words in a dictionary or numbers in a phone book, where you know the number, and it's like instead of starting from the front half of the phone book, instead of starting the front half of the dictionary to the end, if the number's like
One will be the middle of the phone.
yeah, if the word is like a Y word and you started from front all the way to the end, it would take a super long time. So using this kind of like bisection, it's like, okay, well, let's start dead in the middle, right? That's our node. If that's the word we're looking for, great. If not, let's like, is it sort of like on this side or this side? And it's like, okay, so you started the node and then it's like, okay, let's go left or right. And it's not, it's a little different than I guess what I think Avi's describing here, but that's the first thing I thought of when I saw like, the prefix processing. You start with the node you're on, and then you go left or right accordingly to kind of get to the solution. And
So like each level of the tree, you're halving the work you have to do to find it.
so it's, that's like a common strategy to, at the end of it, the average amount of time it'll take to find any given word is a lot less than if you had to go with full iterative play. Especially if you have a lot of words. Like the more n goes up, the more efficient that actually tends to be.
Kirk is right. If this is an ordered binary tree such that the left nodes are less than whichever, those numbers will have to be ordered, but the then anything in the left subtree is smaller than the node, which holds true recursively, then that's one way to search. Yes. I would rather not complicate further. You can do many things with binary trees, but the concept is you would traverse it either node left subtree, right subtree, left subtree node, right subtree, left subtree, right subtree node. Basically, this is what I was trying to impart in this slide. And I have one more point. Are there any more questions before I go to my last point? Okay. If the operation that we need to do does not follow prefix, infix, or postfix processing, then this tree structure is not the right tree structure. So for example, if the problem at hand is for a given depth, let's say depth 2, itemize 4, 5, 6, and 7, then this tree structure is not the correct tree structure. You'll need to come up with a better tree structure for that problem. Does everybody understand my last point?
Yeah.
Okay. At this point, I'm done with the slides. We've gone through 6 slides, I think in about an hour plus, which means my estimate of 20 minutes was a horrible estimate. Please forgive me.
I think it was a great presentation.
Oh, thank you, thank you, thank you.
I'm going to
Megan.
stop the recording here.
Okay.